Good evening, everyone. In the last lecture, we discussed about the potentials and we completed the topic potentials. Now we'll be applying the same topic in understanding the concept of electrical capacitance or the capacitors, right? Let's suppose that we have a conductor here. This is the conductor. And we are supplying some charge Q on the surface of this conductor, right? And because of this charge Q on the surface of this conductor, the conductor has some potential, right? Let's suppose this is a spherical conductor. Then the potential on the surface of the spherical conductor will be nothing. That will be kq upon r, right? And r is the radius of this conductor, right? So it means that the potential of this conductor depends upon the charge supplied to the surface of this conductor. Greater the charge supplied to the conductor, greater will be the potential on the surface of this conductor. And if we talk about the electric field due to this conductor, it will be nothing. It will be equal to kq over r square. And near the surface of this conductor, the electric field will be nothing. It will be kq upon capital R, right? So it means that greater the charge supplied to this conductor, greater will be the potential, right? And let's suppose this charge Q is supplied to this conductor. It means that this potential has to be directly proportional to the charge Q supplied to this conductor, right? Now, greater the charge supplied to this conductor, greater will be the potential, right? So it means that, let's suppose that it means that V is directly proportional to the charge Q. And if we replace this proportionality here with some constant C, let's call this constant C. So V is equal to CQ, or we can write C as Q upon V. Here C is nothing, it's a constant. It's a constant. So let's try to understand what this actually electrical capacitance is. So does it mean that we can supply any amount of charge on the surface of this conductor? Does it have any limit? How much charge we can actually supply to the surface of this conductor? If we supply the charge Q, if we increase the charge continuously, it means that the electric field strength is going to increase and the potential is also going to increase, right? It means that after some time, the electric field strength will increase to such extent that we will no longer be able to supply the charge to the conductor, or the charge or the conductor cannot retain any more charge, right? Because of the medium present outside this conductor, there will be some medium. Let's suppose air is present outside this conductor, right? Air is the medium outside this conductor. Now what this conductor will do, the electric field strength is going to increase upon the supply of the more and more charge. So it means that it will apply more force on the molecules of this air, right? Molecules of this air. And because of this force, the molecules of this air will get polarized. The molecules of this air will get polarized, and it will be the negative pole of this molecule will be towards this positive charge, right? And the negative pole will be towards this opposite to this positive charge, right? So this is how the molecules of the air are going to get polarized after some time, right? Because of this electric field strength. So it means that dipoles will be created, right? These will be the molecular dipoles here. These are the dipoles here. And these dipoles are created, or we can say the air is polarized because of this electric field strength of this conductor, right? Because of this electric field strength of this conductor. So it means that more and more electric field is outside this conductor, the more the air molecules are going to polarize, and there will be a time when the dielectric breakdown will take place. Dielectric breakdown will take place. Dielectric breakdown will take place. And once the dielectric breakdown takes place, then the negative poles and the positive ends of this molecule will be separated, right? And it means that after that, the negative charge of this molecule will be attracted towards the conductor, and the positively charged and the positive charge will be repelled by this conductor. It means that after that, whatever charge we'll supply, it will be neutralized by these negative charge. It will be neutralized by these negative charge, or we can say that these positive charge because of the dielectric breakdown will try to move away from this conductor, or we can say that this conductor is going to leak charge, right? Conductor leaks charge. So it means that how much charge we can supply to a particular conductor, it depends upon the dielectric strength of the medium, dielectric strength of the external medium, right? If the dielectric breakdown takes place, then we cannot supply more charge. It means that this conductor will not retain more and more charge because that dielectric breakdown has taken place, and if we supply any more charge to this conductor, the charge will be leaked into the medium, right? The charge will be leaked into the medium, and due to this, the medium will become conducting, right? Medium will become conducting, or we can say this dielectric medium will now conduct charge, and the charge will be flowing, right? Or we can say this conductor is going to leak charge, right? So it means that the amount of charge we can supply depends upon the medium. It depends upon the external medium, right? Or we can say depends upon the dielectric strength of external medium, right? Now let's suppose Q charge has been supplied and dielectric breakdown has not taken place. Then the charge Q supplied per unit potential, charge Q per unit potential, right? There will be a potential on this surface, and the charge Q, charge per unit potential, we call this as capacitance. This is nothing, we call this as capacitance, right? There's a difference, there's a very important difference between the maximum charge holding capacity, right, and the capacitance of a conductor, right? Maximum charge holding capacity, or the maximum charge that that conductor can hold on its surface, it depends upon the external medium also. It also depends upon the size and shape of a conductor also, right? But if we supply a charge Q to this conductor and the potential V is developed on this conductor, then the Q upon V will be the capacitance of this conductor, right? So it means that capacitance is Q upon V, the charge Q on the conductor and the V potential on this conductor, right? And let's suppose if 1 coulomb of charge is supplied on the surface of this conductor and the potential of 1 volt is developed on this conductor, it means that capacitance will be equal to 1 coulomb per volt, or we call it as 1 farad. This is also called as 1 farad. So 1 farad is the SI unit of this capacitance of a capacitor, right? That's why we define it that it shows the capacity of a conductor to store electric energy. We'll come to it, how the electric energy is actually stored in a capacitor, right? But the potential on the surface of this capacitor, the potential on the surface of this conductor depends upon the charge supplied to this conductor, or we can say that the dielectric voltage decides how much charge we can supply to the surface of this conductor, or how much charge the conductor can retain, right? After that, there will be a dielectric breakdown, right? So the maximum electric field strength, so that there will be no dielectric breakdown, we call that as electric field breakdown strength of electric field, so that there will be no breakdown, right? So dielectric strength is nothing, is the maximum value of electric field which can be tolerated by a medium without the dielectric breakdown, right? Let's suppose that for air, the dielectric strength is 3 into 10 to the power 6 Newton per coulomb. This is the electric field, right? This is the field strength for a air. So if we supply a charge to a conductor to such extent, right, to such extent, so that the electric field near the surface of this conductor becomes 3 into 10 to the power 6 newtons per coulomb, right? 3 into 10 to the power 6 Newton per Coulomb. After that, what is going to happen? The dielectric breakdown will take place. It means that there will be two poles of the charges here for this medium. One will be the negative pole, another will be the positive pole, or we can say dipoles will be created. And this medium is going to break, and the negative charge of this dipole is uh, going to fall on the surface of this conductor, and the positive charge is going to move away from this conductor, right? That's why we say that if any further charge is supplied on the surface of this conductor, the conductor is going to leak the charge, right? The conductor is going to leak the charge, right? So the conductor will leak the charge. So that's what we call as dielectric strength, or we can say uh, dielectric potential strength, right? Dielectric potential strength. So this is the maximum potential that can be there on the surface of the conductor so that dielectric breakdown does not take place. So it means that let's suppose Q charge has been maximum we can supply Q charge, right? We can supply Q charge. Charge we can supply to the surface of this conductor, right? Then this maximum charge that can be retained on the surface of this conductor will be the capacitance of this conductor multiplied by the maximum maximum dielectric potential strength. Let's call that as Vmax, right? Vmax. So this is the maximum charge that this conductor can hold, right? That this conductor can hold. So this is the maximum charge, right? Maximum charge holding capacity. Maximum charge holding capacity. If we define the capacitance of a capacitor, it will be nothing. It will be charge supplied to the capacitor and the potential on that capacitor, that is Q upon V. That will be the capacitance of that capacitor, right? But what about the maximum charge holding capacity? That will depend upon the dielectric strength. That will depend upon the shape of a conductor or size of a conductor as well, right? So we'll discuss all these things one by one. Let's see how the dielectric strength depends or dielectric strength depends upon the shape of a conductor. Let's suppose that we have this isolated conductor here, right? We have arbitrary shaped isolated conductor here, and we are supplying a charge Q to this conductor, and this charge Q will be distributed on the surface of this conductor, right? Let's suppose Q charge has been supplied to this conductor, right? Now this conductor is not a regular conductor. It's not a regular shaped conductor. It's an arbitrary conductor, irregular shaped conductor. It means that at each and every point, the radius of curvature of this conductor will be different, right? Suppose we take this point. If we assume that this point is a part of some circle, right, then the radius of curvature for this point here will be like this. So for different points, the radius of curvature will be different. Or we can say that for isolated conductor, the charge density actually depends upon the radius of curvature at that point, and it is inversely proportional to the radius of curvature on an isolated conductor. By isolated conductor, we mean that there is no any other charge or any other conductor in the vicinity of this given conductor. So the charge density will be inversely proportional to the radius of curvature at any point on this conductor. It means that for the point where the radius of curvature is less, then the charge density at that point is going to be more. The charge density at that point is going to more. If the charge density at that point is greater, then the electric field at that point will be sigma upon epsilon naught. It means the greater the charge density at some point on a conductor, the greater will be electric field strength, right? So it means that electric field strength depends upon the radius of curvature at some point on the surface of a conductor. And similarly, that's the reason at a points where the radius of curvature is less, there's a possibility of greater electric field, or we can say at that point the dielectric breakdown may take place, right? The dielectric breakdown may take place, right? So it depends upon the shape of the conductor as well, and the radius of curvature, right? Let's suppose we are taking this regular sphere, right? Regular sphere of radius r. This is a regular sphere of radius r. Now you can say that it's the radius of curvature at each and every point on the sphere is same, or we can say that sigma here is constant at each and every point, because for this conductor here the radius of curvature is same for each and every point, And for this conductor, if we compare the two conductors, it's more likely to have a dielectric breakdown in conductor first. It's more likely to have a dielectric breakdown for conductor first than conductor second, because the radius of curvature for the conductor first is different at different points, and where the radius of curvature is very less, then the charge density at that point is going to be more, and the electric field strength will be more at that point. And it's very likely that this conductor, for this conductor, there can be a dielectric breakdown, right? Rather than this regular shaped conductor, right? So it depends upon the shape of a conductor, and directly we can say that it depends upon the radius of curvature of a conductor for an isolated conductor, right? So that's how it depends upon the how the charge holding capacity depends upon the dielectric strength, and in particular that dielectric strength depends upon the shape of a conductor as well, right? And the size of the conductor as well, right? Because for different size of conductor, the potential will be different, or electric field strengths will be different. That's the reason we say that it depends upon dielectric strength, or the maximum charge holding capacity depends upon the shape of the conductor as well. It also depends upon the size of the conductor as well. Let's take, for example, let's suppose this is the sphere of radius r, and this is another sphere of radius 2r, right? 2r, and we are supplying the same charge q and q here. The potential here for the first case, let's call this as sphere A and this as sphere B. For the sphere A, the VA is going to be kq upon r, right? Kq upon r. And for sphere B, the potential is going to be kq upon 2r. And you can see that here in this case, for the sphere B, the dielectric potential is less, right? The dielectric potential strength is less, can be less as compared to the sphere A. It means it's less possibility of having the dielectric breakdown in sphere A rather than sphere B, because of the less electric strength in case of sphere B as compared to the sphere B, right? So that's how it depends upon the size of the conductor as well, right? Now, one more point is that let's suppose that we want to find the capacitance of an isolated conductor, right? And let's suppose this is an isolated conductor, and we are bringing some charge q from the infinity, right? From the infinity, we're supplying the charge q. From infinity, we're supplying some charge q on the surface of this isolated conductor here, right? Spherical conductor, isolated spherical conductor here, right? The charge plus q has been supplied to the surface of this conductor, and the radius of this conductor is equal to r, and the radius of this conductor is equal to r, right? So it means that the potential on the surface of this conductor will be nothing, that will be equal to kq upon r, right? Or we can write it as q upon 4 pi epsilon naught into r. Let's suppose that the outside medium is air, or we can say that dielectric constant of air is equal to 1, right? So the potential on the surface of the sphere is going to be q upon 4 pi epsilon, right? That's the potential. So if this is the potential on the surface of this sphere, right, and the charge q is applied, then the capacitance of the sphere will be q upon the potential, right, on this sphere, right? Here the reference for this isolated conductor is always taken to be infinity, right? But the reference for the isolated conductor is taken to be infinity, and we assume that at infinity the potential is uh, equal to 0, right? Potential at infinity is equal to 0. If the potential at infinity is equal to 0, then the potential difference between the 2 points between the surface of this spherical conductor and the point at infinity will be equal to V, right? So that V is nothing, that's equal to q upon 4 pi epsilon naught r, right? So q and q will get cancelled, will be left with 4 pi epsilon naught, right? 4 pi epsilon naught. The capacitance of spherical isolated capacitor, right? That this is what we call as self-capacitance. This is also called as self-capacitance, right? Why self-capacitance? Because there is no any other conductor in front of this capacitor. So this is what we call as self-capacitance of a conductor. So this self-capacitance of this conductor is equal to 4 pi epsilon naught r, right? And in presence of medium, in medium of dielectric strength, equal to, or we can say medium of dielectric constant equal to epsilon naught r, epsilon r, then the capacitance will be equal to 4 pi epsilon naught epsilon r multiplied by the radius of this capacitor, right? So this is the capacitance of a isolated spherical conductor, right? In presence of medium and in presence of air as well. And we can see that this capacitance of this isolated conductor depends upon the radius of this sphere, right? So you can see that it is directly proportional to the radius for this sphere. It means that it depends upon the size of a conductor, right? Now what happens if we place two conductors? Let's suppose we have two conductors here. Let's suppose we are placing two conductors. This is conductor 1. Let's suppose this conductor is of positively charged conductor, right? Positively charged conductor. And let's suppose the potential on this surface of this conductor is VA, and this is a conductor A. And we are bringing close to this conductor another conductor, right? And this is a negatively charged conductor, right? Negatively charged conductor. Negatively charged conductor. And let's suppose the potential on the surface of this conductor B is VB, right? Let me call this as conductor B. Now we have to see what is going to happen to the capacitance because of the presence of another conductor near the surface of this conductor A, right? You can see that conductor B is having a negative charge. The potential due to this negatively charged conductor will be a negative potential. And for this positively charged conductor, the potential will be a positive potential, right? Or we can say that on the surface of this conductor A, right, there will be some potential because of its own charge, and there will be some potential because of the negative charge here, right? So it means that if we try to calculate the capacitance of this conductor, the capacitance of this conductor, let's suppose charge Q is applied, right? Charge Q and minus Q here. Then the capacitance of this conductor will be the charge Q upon the potential, and the total potential will be the sum of potential because of its own charge and the potential because of this negative charge here. It means that the total potential is going to decrease because one potential is a positive potential, another potential is a negative potential, and overall the potential is going to decrease. It means that if the potential decreases for the same charge Q, then the capacitance increases, right? So capacitance increases in this case. In this case, capacitance of a conductor increases. Capacitance of a conductor increases. So it means that as compared to isolated conductor, the two conductors always have more capacitance as compared to the isolated conductor because of the reduction in the net potential difference between the two, because of the presence of the two conductors there. The total capacitance of the capacitor increases, right? The total capacitance of a capacitor increases, and the electric field lines are going to be like this. So the electric field lines will originate from this positively charged capacitor and terminate on this negatively charged conductor, right? Or we can see the net capacitance here increases, right? Net capacitance in this case increases. The net capacitance increases here, right? So the total capacitance, because of the presence of another negatively charged capacitor, negatively charged conductor, the total capacitance increases, right? So let's see how, if we have two conductors of different charge applied to it with different capacitances, right? We have two conductors here. The conductor 1 is having capacitance C1 and the charge Q1, and conductor 2 is having capacitance C2 and the charge Q2. And the potential difference on this capacitor is given as V1, and on this conductor it's given as V2, right? Now what happens is that we are connecting these two conductors with the help of some wire, right? We are connecting these conductors with the help of some wire. And because of this connection, there will be a charge redistribution that will take place between these two conductors, and we have to see how the sharing of charge is going to take place, or we'll calculate the common potential. So finally, the potential of both these conductors will be same, and we will try to calculate the common potential between these two conductors, right? And one more important point is that the total charge is always conserved, right? The charge before sharing and after sharing will be same. Sum of total charge will be same, right? And Q1, and let's suppose Q1 and Q2 is the initial charge, and Q1 dash and Q2 dash is the final charge. So from the here, it means that Q1 plus Q2 has to be equal to Q1 dash plus Q2 dash, right? Q2 dash. And the capacitance of both the conductors is C1 and C2, right? C1 and C2. And we can write this C1 as C1 will be equal to Q1 upon V1, and the C2 will be equal to Q2 upon V2, right? Q2 upon V2. So it means that Q1 dash will be then equal to, or we can say, C1 is Q1 upon V1 and C2 is Q2 upon V2, right? Now the final charges are Q1 dash and Q2 dash, and this Q1 dash will be equal to final potential V, right? Final potential V and the capacitance C1, and this Q2 dash will be equal to final potential V and the capacitance C2. Let's substitute all these value in the equation first here, and let's try to find out the common potential, right? So Q1 we can write as C1 V1, and Q2 we can write as C2 V2, right? And Q1 dash we can write it as V times C1 and plus V times C2, right? We can take V as common. Taking V as common, the common potential will be nothing that C1 V1 plus C2 V2 upon C1 plus C2. So that's how the sharing of charge will take place, right? This is the common potential, right? If this is the common potential, then the final charge Q1 dash will be equal to C1 times C1 V1 plus C2 V2 upon C1 plus C2, and the Q2 dash will be equal to C2 multiplied by C1 V1 plus C2 V2 upon C1 plus C2, right? So this will be the final charge. So this is how the charge redistribution will take place between the two conductors, and that's how we calculated the common potential in terms of the capacitance of the two conductors. So final potential will be C1 V1 plus C2 V2 upon C1 plus C2. So this is the final common potential, right? So this will be the final charge for both the capacitors, for both the conductors, right? Now let's try to discuss about the capacitance of a capacitor. Here the capacitance of a spherical capacitor, right? And in this case, what we are doing is that there are two concentric spheres, right? One sphere is of radius A, right? One sphere is of radius A, and another sphere is of radius B, right? The first sphere is of radius A, another sphere is of radius B, right? And we are supplying a charge Q. We're supplying a charge plus Q to the inner conductor, right? To the inner sphere. And both these are conductors, right? And what we have done is that we have just grounded the outer surface of this outer sphere. Outer surface of this outer sphere has been grounded, right? If the outer surface of this outer sphere has been grounded, it means the potential of this outer surface of this sphere is going to be equal to 0 because it's grounded, right? And plus Q charge is supplied to this inner conductor. It means that the same minus Q charge will be induced. Minus Q charge will be induced on the inner surface of this conductor, inner surface of this outer conductor, right? Minus Q charge will be induced. And because of that, plus Q charge will be induced on the outer surface of this conductor, right? On the outer surface of this conductor, correct? On the outer surface of this conductor. And that plus Q charge will be neutralized, that plus Q charge will be neutralized by the supply of the negative charge by this earth, right? This earth is going to supply a negative charge on the outer surface of this outer conductor, so that the total charge on this outer sphere will be equal to 0. The total charge on the outer surface of this outer sphere will be equal to 0. It means that outside this capacitor there will be no electric field at all, or we can say the electric field strength outside this capacitor will be equal to 0, right? Electric field strength outside this capacitor will be equal to 0. And similarly, Since this charge has been supplied on the surface of this inner sphere, right, on the surface of this inner sphere, it means there will be no charge enclosed inside this sphere. It means that here also inside the inner sphere, the electric field strength is going to be equal to 0. It means that the only electric field strength will be between the region A and B. It means the electric field strength will be between the outer sphere and the inner sphere like this, and it will be radially outwards, right? So this is how the spherical capacitor, the concentric spherical capacitor behaves, right? So there are two important conclusions. Two important conclusions here are: the first important conclusion is that if we ground outer surface of the concentric spherical capacitor, then the electric field strength outside that sphere is going to be 0. It means there will be no electric field strength outside the sphere. If there is no electric field strength outside the sphere, then there is no chance of dielectric breakdown, right? No chance of dielectric breakdown, because electric field strength outside this sphere is equal to 0. So no chance of dielectric breakdown. It means that if there is no charge of dielectric breakdown, right? No chance of dielectric breakdown, right? So there will be no dielectric breakdown, because outside the outer sphere, the electric field strength is equal to 0, right? And this whole electric field will be concentrated between this region, right? So this region will be concentrated with the electric field. It means that the total energy because of this electric field will be only present in this region only, will be only present in this energy region only, right? So there will be no electric energy outside this sphere, and there will be no electric energy inside the inner sphere. Only the electric energy, electrostatic energy will be present between the region of inner sphere and the outer sphere, right? So the total charge on this inner sphere is Q, right? Q total is equal to Q on this inner sphere. Let's call that as Q, right? And the potential on the outer surface of the sphere is equal to 0, and the potential on the inner surface will be the potential on this VA. Let's call that a VA. That will be equal to potential due to its own charge. That will be Q. That will be KQ upon A radius, right? KQ upon radius A. And the potential due to this negative charge which was induced on the inner surface of this outer sphere, right? That will be equal to minus KQ upon the radius of the outer sphere, right? That's equal to B. Let's call that equal to B. So it means the total potential on the surface of this inner sphere will be KQ multiplied by 1 upon A minus 1 upon B, right? Correct. So the capacitance of this capacitor will be Q upon VA minus VB, right? VA minus VB. And we know that potential on the surface of this outer sphere is equal to 0 because it's grounded, right? Potential has to be equal to 0, right? So the capacitance will be equal to Q, the charge is Q, upon the potential difference, that's KQ multiplied by 1 upon A minus 1 upon B, right? Minus 0, because VB is 0, right? So from here, C will be equal to, we can just cancel out this Q and Q here. C will be equal to, it will be equal to AB, right? AB upon A minus B, right? And there's a factor of K, we can write that as 1 upon 4 pi epsilon naught, right? And that will be equal to 4 pi epsilon naught A into B upon A minus B, right? So this is the capacitance. This is the capacitance of this spherical capacitor, right? This is the capacitance of this spherical capacitor, right? So 4 pi epsilon naught AB upon A minus B will be the capacitance of this spherical capacitor, right? And in this medium, let's suppose if we are placing some medium here, right? We are filling this region here with some medium here, right? If we fill this region with some medium here of dielectric strength epsilon, right? With dielectric strength epsilon r, then in that case, the capacitance will be nothing. Capacitance will be 4 pi epsilon naught epsilon r, right? A into B upon A minus B, right? So this is the capacitance of a spherical capacitor in which the outer sphere of a capacitor is grounded, right? If the outer surface of the capacitor is grounded, then the electric field outside the sphere is going to be equal to 0, or we can say that there will be no electric field outside that capacitor, right? So this is the capacitance of this affair, provided the outer surface of this capacitor is grounded, right? So let's move on to the next concept. The next concept is that we have to find the work done in charging of a conductor, right? We are supplying the charge Q to the conductor continuously, and when we supply the charge Q to the conductor continuously, then the pre-existing charge on the surface of this conductor will definitely oppose the supply of the charge, right? Because of this repulsive force, then we have to do some work because of the external agent to supply the total charge Q. And what is that work? We can calculate that work will be nothing, that is dw, that will be equal to v dq, right? V dq. So v dq will be the total work. Let's suppose we're supplying the charge from q1 to q2. Initially the charge was q1 and the final charge is q2, right? And we know that capacitance of this conductor is nothing, that's q upon v, right? Q upon v, or we can replace v with q upon c, right? We can replace v with q upon c, right? Q upon c. So our dw will be nothing, dw will be equal to q upon c dq, right? Now integrating it on both sides from 0 to w, right? That will be a total work done. And let's suppose the initial charge was q1 and the final charge is q2. Then the work done will be 1 upon c. The integral of q dq will be q square upon 2. That's q square upon 2 with the limits q1 to q2, right? So the total work done in this case will be nothing. It will be 1 by 2c multiplied by the q2 square minus q1 square. So this will be the total work done in supplying a charge to this conductor from q1 to q2. It means the total charge supplied to this conductor will be nothing. That will be equal to q2 minus q1, right? And let's suppose if we are q1 is equal to 0. If q1 is equal to 0, then the total work done will be 1 by 2c multiplied by q square, or we can say that work done will be q square upon 2c. This will be the work done in supplying the charge to this conductor, right, from q1 to q2, right? And this work done will be stored as a energy of this capacitor, stored as energy of this conductor, right? Of this conductor or capacitor, right? Conductor or capacitor, right? So the energy stored in a capacitor will be nothing. Let's call that E. This will be the total work done by the external agent, right? And we calculated that total work done was nothing. That was equal to integral of Q upon C into dq, right? From 0 to Q, right? So this will be nothing. That will be half Q square upon C, right? Or we can write it as Q square upon 2C, right? So this will be the energy stored in the capacitor, right? We can rewrite it as Q square upon 2C, right? Or we can rewrite it as, like, we have Q is equal to CV, right? We can substitute the value of Q in this equation. So it will be C square V square upon 2C, right? Or it will be equal to half CV square, right? So half CV square. So half CV square will be the energy stored in this capacitor, right? For any capacitor, if C is the capacitance, V is the potential difference between the plates of a capacitor, right? Then the energy stored in that capacitor will be equal to half CV square. That will be equal to half CV square, right? Let's try to solve this simple problem here. If the charge in a capacitor is 4 coulomb and the energy stored in it is 4 joules, we have to calculate the voltage across its plates, right? So the energy is nothing. That's equal to half CV square, right? Half CV square, or that's equal to Q square upon 2C, right? It's given that if the charge in a capacitor is 4 coulomb and the energy in it is 4 joules, right? Calculate the voltage, right? Voltage. So we have to write the energy in terms of charge Q and the voltage V, right? We can replace this capacitor C here with Q upon V, right? Q upon V, Q and Q will get cancelled. So it will be QV upon 2, right? QV upon 2 will be the energy of this capacitor, and that's equal to 4 joules, right? If that's equal to 4 joules, then the potential drop will be 4 into 2 upon Q, and Q is given as 4. So 4 and 4 will get cancelled, will be left with 2 volts. It means for this capacitor, the potential drop, the potential or the voltage across its plates will be equal to 2 volts, right? Now let's discuss about the parallel plate capacitors, right? These are two parallel plate capacitors, right? In the previous lectures where we studied about the electric field strengths due to the uh, sheets, right? Due to the sheets. And we also found that outside region for the sheets, the electric field strength is equal to 0, and inside region, the electric field E naught is nothing, that's equal to sigma upon epsilon naught, right? That's the electric field strength inside this region. That's sigma upon epsilon naught, where sigma is the charge density, and the sigma we can write it as Q upon A, where A is nothing, it's the area of cross section, that's equal to area of capacitor, right? Area of capacitor, right? And the Q is the total charge on this capacitor, right? And let's suppose these are the two parallel plate capacitors. One is the with charge plus Q, another is with charge minus Q, right? Two positively charged plates, right? They are separated by a distance T. Plate separation is T, right? And the plate area is given as A, and there is no electric field existence outside these plates. Why is it so? We know that the total electric field cancels out because of the negative plate here and the positive plate here outside this region, right? That's the reason the electric field strength outside this region is equal to 0. It means that once again the whole electric field has been confined to the regions between the two plates, right? It means the whole energy will be now confined, stored in the region between plus Q and minus Q, right? So we know that this is a uniform electric field, right? Uniform electric field. And in case of uniform electric field, we can use this equation, right? The electric field strength is nothing. It's potential difference between the 2 points upon the distance between the 2 points, provided the field is uniform. Provided the field is uniform, we can use this equation directly. If we have a uniform electric field, then we can use electric field as potential difference upon the distance between the 2 points, right? Otherwise, we have to calculate the electric field strength. If this is a non-uniform field, then we calculate the electric field strength using the concept minus del V upon del R, right? Or dV upon dr, right? So that's how we calculate the electric field strength, where the negative sign says that the potential or the electric field is directed always from the decreasing from the higher potential to the lower potential, or electric field is always directed along the decreasing potential, right? Now we have two plates here, plus one plate is with charge plus Q, another plate is with charge minus Q. And you can see that the negatively charged plate has been grounded. It means that it will have no no potential on the surface of this plate, right? And electric field strength is E naught. If we calculate the potential difference between these two plates, the potential difference between these two plates will be nothing. That will be equal to E naught multiplied by the T, right? And E naught is nothing, that is sigma upon epsilon naught, right? Multiplied by T, right? So this will be the potential difference, right? Or we can write this as Q upon A epsilon naught multiplied by this distance T. So the capacitance will be nothing. It will be Q upon V, and V is nothing, that's equal to Q into T upon A epsilon naught, right? Here Q and Q will get cancelled, we'll be left with A epsilon naught upon D, right? A epsilon naught upon D. So this is the capacitance of this parallel plate capacitor, provided there is no medium field. There is the only medium between these two plates is air, right? The medium between these two plates is equal to air, right? And there is no dielectric field between these plates, right? And if dielectric is completely filled between these plates, if it's filled with the dielectric completely, right? If this parallel plate capacitor is completely filled with the dielectric constant of epsilon r, right? The dielectric constant of epsilon r. So epsilon r is the dielectric constant of this medium, right? So this is the dielectric constant of a medium. If the plates are not filled with any dielectric, then epsilon r will be equal to 1, and we will have capacitance as A epsilon naught upon T, right? But if it's filled with some dielectric, with dielectric constant epsilon r, right? Then the capacitance in that case will be A into epsilon naught into epsilon r upon T, right? So this will be the dielectric strength, right? This will be the dielectric, this will be the capacitance. It means that the dielectric medium increases the capacitance of a capacitor. So if we introduce a dielectric medium between the two plates here, the dielectric constant, what the dielectric constant does is that it increases the capacitance of a capacitor, right? So capacitance of a capacitor increases, right? Now let's suppose we have to find the capacitance of a parallel plate capacitor when dielectric is partially filled, right? Now this dielectric is not completely filled, it's partially filled in this region, right? It's partially filled in this region, and we are supplying a total potential. Let's suppose total potential between these two plates here is equal to V, right? Total potential between these two plates is equal to V, right? The charge density of this plate is sigma, and the charge density of the negative plate is minus sigma, and the thickness of this dielectric is equal to T, right? T is the thickness of this dielectric slab, and the dielectric constant of this slab is epsilon r, right? Now we'll be using the same concept, right? Our capacitance is nothing, that's the charge, that's equal to electrical capacitance is equal to charge upon the potential difference, right, between the two plates here, right? Now this total potential difference will be between this region, and we know that in this region, since this is a dielectric, right? In dielectric, the electric field is nothing. Electric field will be sigma upon epsilon naught into epsilon r, right? So this will be the electric field strength within this dielectric, right? If this is the electric field strength within this dielectric, then here there is no in this region, in rest of the region, there is no dielectric. Then this epsilon naught, or we can say the electric field strength, is nothing, that's equal to sigma upon epsilon naught, right? Sigma upon epsilon naught, right? So this total potential, this total potential here will be nothing. Total potential here will be nothing. That will be equal to, so this is the electric field strength, right? E naught, and this is the epsilon naught, that's the permittivity of free space, right? So the total potential will be, some of the potential will be in this region, right? In this region of this dielectric, and rest of the potential difference will be along this region, right? So we can write it as, once again, it's a uniform field. Even within the dielectric, the electric field strength is a uniform electric field strength, right? So it means that the total potential will be so the total this length of this slab is T, right? That's equal to T, and the electric field is sigma upon epsilon into epsilon r. We can write it as sigma T upon epsilon naught into epsilon r, and we'll be left with the potential difference across this unfilled area. So it will be equal to sigma upon epsilon naught multiplied by the distance, that will be D minus T, right? D minus T, right? So this will be the total potential voltage supply. That's sigma T upon epsilon naught into epsilon r plus sigma upon epsilon naught D minus T, right? And we can replace this sigma here with charge upon area. That will be Q upon A, right? That will be Q upon A, Q upon A, right? And we can write this capacitance here. That will be Q upon V. That's equal to Q upon V is sigma T, right? V is sigma T, right? Sigma T upon epsilon naught into epsilon r, right? Plus sigma T minus T upon epsilon naught, right? We can substitute the value of sigma here. We'll be left with Q T upon A epsilon naught into epsilon r, right? Plus Q upon A into epsilon naught multiplied by D minus T, right? Multiplied by D minus T, right? So this Q and Q will get cancelled, right? It will get cancelled. We'll be left with capacitance here. C, that will be equal to T upon A epsilon naught into epsilon r, 1 upon T upon A epsilon naught into epsilon r plus T minus T upon A into epsilon naught, right? So T minus T upon A into epsilon naught, right? We can take 1 upon A epsilon naught as common. We take 1 upon A epsilon naught as common. We'll be left with T upon epsilon r plus T minus T, right? We can take this A upon epsilon naught in the numerator. So we'll be left with A multiplied by epsilon naught upon T upon epsilon r plus T minus T, right? Taking once again T as common, A upon epsilon naught. So it will be taking T as common. So it will be T into 1 upon epsilon r minus 1 plus T, right? Plus T. So this will be the this will be the capacitance of the capacitor, right? This will be the capacitance of this capacitor, which is partially filled with the dielectric slab, right? Which is partially filled with the dielectric slab. So this is the capacitance of a capacitor, which is partially filled with this dielectric slab, right? So if this capacitor is if this capacitor is fully filled, right, it means that T will be equal to D, right? It means that T will be equal to D. T is equal to D. Put the value of T equal to D in this equation. Then D minus D will be 0. Will be left with D only. Then it means that the capacitance at that time will be equal to A epsilon naught, right? A epsilon naught epsilon r upon D, right? So this will be the capacitance of the capacitor if this is fully filled. This is fully filled capacitor. And this is for partially filled. This is for partially filled, right? This is for partially filled capacitor. So this is how we calculate the capacitance, or this is how we calculate the capacitance of a parallel plate capacitor, right? Here we concluded an important point: outside the region of this capacitor, be it spherical capacitor grounded or parallel plate capacitor, the electric field strength outside these capacitors is equal to 0. It means the whole electric field is confined within the region of this capacitor. So that's it for today. We'll be meeting in the next lecture with the concept of series and parallel combination of capacitors, and we'll be also solving some of the problems or questions related to capacitors. Take care till then, and goodbye.